Okay, then welcome everyone. Very happy to have Emanuele speak about permutation patterns today. I'll monitor the chat. If you have any questions, I alert Emanuele to it, but I think it's also fine if you interrupt Emanuele with the microphone.
Yeah, so feel free to interrupt me anytime.
Okay, so the floor is yours.
Okay, so today I will be speaking about a joint project with my advisor, Joscha. And we introduced this term conjoined permutations patterns to, it's more like terminology that we use to remember what we are doing somehow. And so the departure point was permutations patterns, which are somehow play a big role in discrete mathematics. And at the beginning of my talk, I will be talking about them in general, showing some examples, and also talking about the specific patterns, which we call conjoined permutations patterns. Then I will be speaking about two new Hopf algebras that we introduced in order to somehow to index this type of patterns. Okay, and yeah, so let's start from the introduction. So as I said, permutations patterns, they play a big role in many fields of math, and I will be showing an example of them arising in statistics. So with the Oeffting's independence test and how they can be used to compute this kind of statistics, and also about the main source of inspiration for our conjoined permutations patterns that is based on permutation entropy, which is an index that people use to determine the behavior of a discrete time series. And I think Yannick is also here, so I will also be speaking about Hopf algebra on permutations patterns that was introduced 10 years ago, which index these kind of objects. So let's start from this Oeffting's independence test. So whenever we observe two random variables, the natural question in statistics is asking whether these two random variables are independent. And this quantity that you see here is simply the integral over the difference between the joint distribution and the product of the marginal. So it measures somehow the distance of the independence between these two random variables. And yes, we have a sample that is given by this bivariate data. Okay, so there are pairs of data. And it turns out that you can rewrite these integrals as an integral in 5 variables. And you can estimate this quantity with this expression, which is just an average. Okay, it's a sum of products of indicators. And so these alpha, these indices are given. So we are summing over all combinations of subsets of size 5, taking into account also the order. That's why we are also dividing then by this number, n times n-1 and so on till n-4. And the interesting part about this statistic is that it only matters the only thing that matters is the order of the value. Okay, so clearly, if we consider the order of the x and the order of the y, this induces a permutation, right? Induces a permutation that of size n. And so we can have also different data values. The only thing that matters is the order. And it turns out that this kind of expression, so the summation at the numerator, can be rewritten only in terms of the occurrences of certain permutations patterns. Okay, so these numbers that you see are really occurrences of permutations of order 5 in this in the permutations that is induced by the data. And so not all permutations are of order 5 are involved. You can see that, so I'm using one line notation, and so the 3 always gets mapped to the 3. And to get an intuition on why this happened, you can see that so alpha 1 needs to be equal to needs to correspond to the third value, because you see x alpha 1 has to be between alpha 2 or x alpha 2 or x alpha 3, or it has to be between x alpha 4 and between alpha 4 and alpha 5, or with the order reverse. So it's leaving 2 values to the left and 2 values to the right, and that's why we need to so only the third value somehow gives a non-zero. And it's just to give you an idea on why only these patterns appear. And then the author uses this rewriting of this statistic in order to speed up the computation of this statistical test. Okay, now I will show another example of how permutations patterns are used. So there is this very popular paper from also a professor in Bandt that introduces the concept of permutation entropy. So whenever we consider a time series, for example, with a finite time horizon, we can really just compress it and reduce it to the order of its values. And so one way to understand this behavior is to simply consider consecutive patterns. So for example, I only consider the consecutive patterns of length 2, okay, and I just look at the inversion or the time that this time series increases. And this is done for for different choice of n. Okay, so there is a permutation entropy of order 2, of order 3 until order n, and it turned out to be a very successful tool in time series analysis. And here I'm using this notation, so we really take the values on the time series and then we standardize them so that we really have a pattern of size n. Okay, and so this index is simply, so we need to compute the frequencies of these patterns, and then we compute, so this is Shannon's entropy, okay, and we average over these patterns, and somehow there are 2 extreme cases that we need to take into account. So if our time series is monotone, so it's increasing or decreasing, we have that we only observe one kind of pattern, so we have a 0. While if all the elements in the symmetric group of size n are, so if they are equiprobable, we have maximum entropy, okay, logarithm of n factorial. And this tells us, roughly speaking, also how random is a time series. And these were, so somehow this example for us was really motivating this kind of consecutive patterns, okay? And but our so our field is algebraic combinatorics, and permutations already appear in the literature. So the most famous example probably it's the Malvenuto-Rothenauer of algebra. So these 2 authors, they introduced 2 non-commutative products on permutations. And here, so instead of giving the definition, I just provided the visual example. So in this case, when we consider this first product denoted with star, so we somehow shuffle 1, 2 with 2, 1 on the y-axis. Okay, so you see that the black dots always stay to the left and the red to the right, and we're shuffling them vertically, and the relative order of the dots of the red dots and the black dots stay the same. And while the other operation, so with the star prime, we are shuffling horizontally. And so that we have always, so these are graded operations, so we always have permutations of size 4. And you can already see from these examples that these both these operations are clearly non-commutative. And Vargas somehow put this together. So in the paper in which he introduced these Hopf algebra and permutations patterns, and we have that the shuffling now occurs in both directions. Okay, so horizontally and vertically. So you can see that we have a richer expression for the same permutations. And here I denoted also some multiplicity. So the occurrences of these 2, 1, 2, and 2, 1 in these permutations 1, 4, 3, 2. Okay, it happens 3 times with this product. And okay, so back to Yannick. So in his papers, he introduces this shuffle product on permutations, commutative shuffle product, but he also introduces a variant where the underlying pairs can overlap. So if we take 2 permutations, one of size m and the other of size n, we sum over all permutations such that the underlying so these subsets of the ground set somehow need to cover the size of the permutations. And also when we standardize the induced permutations, they need to be equal to sigma and tau respectively. And together with this other operation, that is a sort of concatenation, so that we put, again, here I'm using one line notation, so sigma concatenated to tau, and we are scaling the values of tau of the size of the permutation sigma. And we have that this superinfiltration product together with this other operation forms a connected filter at Hopf algebra. So there is a bi-algebra kind of compatibility. And this product turns out to have also an interesting, for us, combinatorial meaning. So if we consider the occurrences of sigma in lambda, that I denote here with PC of lambda, so comma sigma, we have that there is an algebra morphism, okay? So this, we can think of this map parameterized by lambda as a character, okay? There is an algebra morphism from this Hopf algebra on permutations patterns to the ground field. And to show concretely why this works, I cooked up a small example, so that is somehow extreme. So we can take the extreme case where the pattern that we want to observe is 1, okay? And in this case, there are not so many things that can happen somehow, and so first, so clearly the 1 we observe it on all the so everywhere somehow. So on 1, 2, 3. So here I depicted really the cardinality of the underlying set of the indices, and now we take the Cartesian product of these 2 sets, and the next step is to take a partition of this pair that is based on the type of pattern that they form when we take the union of the elements in these pairs. So really to visualize this, we have, so in purple is 1, 1, where they collapse somehow, and then it can happen that either we see the pattern 1, 2, or the pattern 2, 1. And this is what you can see here. So we see the pattern 1, 3 times, the pattern 1, 2, 4 times, and the pattern 2, 1 only 1 time. But the really interesting part is not so much the number of times that we observe, but the fact that we have these coefficients. Okay, so these 2 in front of the occurrences of 1, 2 in 1, 3, 2 tells us that there is really like a general scheme. Okay, and this is why this thing works. Why this we have that this PC lambda is really algebra homomorphism for this product that Yannick introduced. And now we can talk about conjoined permutations patterns. So the idea was to put together what Yannick did on its Hopf algebras, together what Bandt did on time series. So we want to look not just for permutations patterns, but also at permutations patterns where we ask some of the values so to be consecutive in time. So we specify that, for example, the first n1 values needs to be consecutive, and then there can be an arbitrary gap between the n1 plus 1 from 2 and 2 values, and so on and so forth. Okay, so we have these blocks, and the values need to be consecutive in time. So as it's the case when we wanted to calculate the permutation entropy, okay, so where the values were consecutive. And to provide, again, a very simple example, consider the pattern where, so here I use this notation with the bar, so 2 and 1 are consecutive in time, while 3 can be far apart as much as we want. And the main pattern is, so the large permutation is permutations of order 6, and we have that in the first two cases, somehow this is fine because the 2 and the 1 are consecutive, while in the third case, this is not compatible with the counting we're asking for. And the idea was, so first, how to encode this? Well, the most natural way is for us was to store it as a pair. So where sigma is a permutation and S is an interval partition of the numbers from 1 to n. And so thinking about how to encode this, we also decide to take a closer look at interval partitions from a combinatorial and an algebraic point of view. So that's why we introduce, so before introducing the Hopf algebra on this type of patterns, I will be speaking about a new Hopf algebra we introduced on interval partitions. So the main building block for this Hopf algebra interval partitions is a binary operation that we defined on interval partitions. So consider the case in which I and j are both finite interval partitions. We define a relation on their union. So we have these blocks, and we say, well, the blocks are in relation if and only if the intersection of the block is empty. And then what we do is we take the closure, so the equivalence closure, so the smallest equivalence relation, which contains this relation. And here you can see in the picture the R, okay? So we have an interval partition, so the blocks are intervals, and 2 is in relation with 2, 3, 2, 3 with 3, 4, and so on. So when we take the closure, somehow all the guys that are in this connected component, they end up being in the same block. And then here it's not illustrated. We simply take the union. Okay, so that we have again a set of intervals actually. So we proved, and maybe it's a lemma, so it's quite straightforward to see that if I and j are both interval partitions, then the result of this binary operation is an interval partition. And additionally, we also proved that this operation is associative, which is important because somehow we want to introduce product and co-product which are associative. So yes, so let's talk about now the products and the co-products. The main operation is defined in a way that it's reminiscent also of the operation that Yannick introduced. So we take interval partitions of n, and then we define a coproduct that is summing again over pairs such that their union cover the ground set. And then the further step is to consider pairs of interval partitions, where here IPA denotes that, so means that I is an interval partition of A. So and I prime is an interval partition on A prime, and then we ask for the gluing to be equal to this this interval partition S. And there are, of course, so for the same pairs of A's, there are also different choices of I and I prime. And the last thing that we have to do is, since the underlying vector space is the one of we call them standardized interval partitions, so interval partitions of sets that are of the form that you see here, so positive integers from 1 to n, we need to do a standardization operation. And this is because somehow while S clearly is an interval partition, of course I can glue two partitions that are not looking like S, so to speak. And then the standardized operation, it's so I see questions in the chat, but
yeah, so one question was about the typo. I answered, and Darish asked whether these intervals should be extrinsic or extrinsic, i.e., can an interval in I cross over a gap in A?
What is meant by cross over a gap? I don't.
So A can have some gaps because it's just a subset of n. So an interval in A can be something like 3, 5. If 4 is not an A, the question is to allow this. I.
So I is not an interval; it's an interval partition of A.
Right, but can an interval in I be something like 3, 5?
No, so not in the same block. So it can be 3. So 3 is in one block, and 5 it's another block. This can happen. Yes. So this can happen. And the standardization, again, it's just making sure that these objects are sent back to this to the space. And here, so we will see that there is also somehow a formal justification. We can really draw the interval partition. So, for example, the single block with squares. And in this expression, so you see the primitive part. So when you have somehow the empty set with the partition, and then also other terms where, so in the next slide I will explain maybe intuitively why, or actually so in detail why these two, for example, appears here. But you see that there is somehow some sort of gluing operation, because, for example, in the last guy you have also the singleton partition and of 1, 2, and clearly with this gluing gluing the singleton with the single block will give you the single block partition. So this is the term that has to happen. And while, for example, if we had to compute the coproduct of the singletons, we would never observe the single block, because this gluing operation somehow is always is never making you finer. Okay. And the other operation that we introduced is closer to the other operation from Yannick. So here we have that S is again an interval partition, and I'm writing down the N1 block of S. And the same I do for T. So these are the N2 blocks of T. And this operation is defined somehow by scaling the blocks of T by the size of S. So we take the union of all the blocks, the cardinality of the underlying set, and we scale T. And clearly you have that this is so This is also associative, so it was somehow more straightforward. The other guy is also associative because of this gluing operation so we proved that it is. And it's clearly also something that lives in the space of this standardized interval partition. And to see the numerology here somehow for this bullet operation is really straightforward. So we have that we are really somehow putting side by side these interval partitions, while the structure for the for this product is a little bit more complex. So here, very concretely, so if we take we can really see the section coefficients. So we are considering the cardinality of this set, and if we take this this interval partition and we require the I to be somehow equal to this single block and I prime to be equal to the singleton, the only choice that we have is so 1, 2, because it's the only time that you observe a single block, and then we have two choices, so we can pick either 1, 3 or 2, 3, since we need to cover somehow the entire set also. One second, I can't move my slides now for some reason. Let's see. Okay, and so this operation is compatible with the coproduct of this sort of concatenation of interval partitions, and it forms a bi-algebra. And since so the spade operation is filtered while this other is graded, together they form a connected filtered Hopf algebra. And so it is a commutative Hopf algebra. So we know from the literature that so as an algebra, it is isomorphic to some polynomial algebra. And we can actually give so a description of this object in terms of words. So which is somehow was already given by drawing these squares. So if we take the free vector space on the positive integers, and we can define on the generators of the tensor algebra, so in this case really n, we can ascend each integer to the single block partition, and if we take the unique extension of this map, then this is the linear isomorphism. Okay, it maps from basis to basis, and this product that we have, we can really so we can really think of words on positive integers, and also this other operation, this filtered operation, we can express it as a product on words. And so we have that this relabeling of our product together with the concatenation in the sense of the concatenation of tensors is also Hopf algebra, which we can somehow think of, it's really the same Hopf algebra. So it's just a relabeling of what we have. And so one interesting question for us was, of course, the coproduct is straightforward, so we could implement it immediately. But it was interesting also to look to see if there was a possibility to give a recursive definition for this product. So we start by defining on the empty word, so from taking the product from the left and from the right, and then we define recursively. And here, so again, I drew a picture, so I hope it's understandable. Somehow you can, so I drew images on top of equations that are examples of this recursion. Okay, so the first part of this recursion is the shuffle part. Okay, so it can happen that Tn is the last letter, or Sm, and somehow it doesn't overlap with Tn. And these drawings represents, so the last letter here, for example, is the red one, and then we would have to recursively, so iterate the definition on the remaining guy. And the same also for the other guy in this summation. So they are both shuffled. So the rest of the recursion is slightly more complicated. So what could happen is somehow is that the two blocks could overlap in the sense that they could be glued together, but there are actually not so many things. So what we need to take into account with this expression is, so we have this function that has 5 parameters that will also be shown, so computed recursively through an example. So the first input is the first word, the second is the other word, and then when we consider these guys on the right, there are 3 parameters. So we have their length, which in this case would be 7, 5, and 4. Then we need to take into account somehow if there is the possibility for, so what is the, so we chose this word overhang. So if in the first example to the left, for example, you have that you could stack this red word because of using this gluing operation, and then you would iterate. While in example in the middle, for example, you could do it with the green one. There is also a third case, which is the one, so the one to the right, where somehow there is no overhang. So in this case, you would simply iterate and you would take the definition of the product again on the remaining cases.
Emanuele,
yeah.
Coach asks, what was theta? What is theta?
Yeah, I show now an example. So I didn't give somehow the explicit recursion because it was a little bit cumbersome, but I can explain. So try to explain intuitively how this works. So you have, as I said, so the first 2 arguments are just the words, and then here we have 3 parameters. And instead of somehow writing them down, you can see them with the picture. So the length of this guy on the right is, you can think of it as, it's really just the length of this block, okay? But in this block, we also want to keep track of the information of which word can be stuck. So in this case, there is room for the red word, not for the green one. And also how long is this room in which we can stack this red word. And this theta is also defined recursively because now we can, so the first thing that we do is we can consider this block here and somehow not stack the last red letter. So here I drew it in transparent, so to say that we forget about its structure and we just shuffle, or we can stack this red letter in 3 different positions, which will give us a different overhang. And you see that the length of of either one of the 2 words will decrease. So that's why it works. Okay, so we are really recursively computing this product. And now the question is, what is, so here I call signature. So what is the analog for partitions? So when we think about permutations patterns, so it turns out that we can also find some sort of interval partitions patterns, which turn out to be a trivial form of counting, but which was somehow necessary to introduce this Hopf algebra on conjoined permutations. So in this case, we introduce a family of functionals which is indexed by interval partitions, and what we count is really the occurrences of induced partitions by these subsets such that they are coarser of this pattern. So S here is also an interval partition. Okay, we are counting and we take care that what we observe needs to be coarser than the pattern that we choose. So here I show what this so what is induced partition is. So in the case we have a unique block and we take 2, 3, 4. So you can see this operation is quite simple to grasp. So you have again a single block since you've taken consecutive numbers. And this is done because we want to really encode this conjoined stuff so that the time points need to be consecutive. So here, for example, this would be cursor. Then, so if we had as a pattern the first 2 to be consecutive and the third to be arbitrarily far apart, this would be a match because this would be, if we observe this as consecutive, would be counted. Okay. Well, the other direction. So if the pattern was a single block, we wouldn't count. Of course, it's this other one. And so we have introduced these functionals, and there is a scenario in which it's quite simple to count, and you can actually visualize it through this example. So in case L is a single block, we can think of of S, which is these 2, 1 interval partitions. We can see that this constellation that I drew here are in bijection with the weak compositions. So the 3 weak compositions of 4. Okay, so here you have 2 blocks. So you have somehow 3 choices, and including the choice of the 0, but the end result of the summation needs to be 4. And this is always the case. Okay, so it's quite trivial somehow. And this was useful also to make some computation to check then the theorem. So we have again that these functionals, they behave well. So with respect to this time to this product. And this was really the identity that I showed you at the beginning with the permutations patterns, while here it's with this kind of operations, and L, S, and T can be any interval partitions. So a sanity check can be done in the case in which all these are single blocks, because we know that, so the left-hand side, again, it's just, so we are counting weak composition of some kind where, so we have an explicit formula. While on the right, somehow the thing we can do is this product, when we consider single blocks, is trivial. So it's simpler. So there are something that can happen. So either these S and T, they do not overlap, or they overlap, or somehow the larger one swallows the small one. And then we can check so that these 2 expressions coincide. And this is just a sanity check for a simple scenario. I try to give now so an intuitive explanation of this character or signature property. So here we have really what it means. Okay, so we have a product of these numbers, and then we can really compute this product and evaluate this map on this linear combination of interval partitions. And here, for clarity, I also labeled the underlying set, so ABCD, so that we can see really what happens. So in the first case, we are clearly counting 3 with the single block partition, while when we take that the gap can be arbitrary, we count 6. And now it's slightly more subtle than before, in the sense that we cannot simply take the union, because in order to have these symbols in the linear combination, we so in the first case, when we take ABC as the union, we also ask what is the result of the gluing operation that is applied on the induced partitions. And in this case, we would have, for example, that if we take as sets AB, AC, and AB and BC, the resulting partition would be the same. So this is something I omitted from this example, but you could have also A on its own and BC together. Okay, so you have to also to introduce this constraint that the gluing of these pairs, not just a union. And also the thing that somehow is slightly different, and is that you really count using these symbols, and the in this other case where we count ABD, so clearly the partitions that is induced by ABD is not the same as the one induced by ABC, because ABC are consecutive, but still they are count the same because of this gluing operation and of this pattern that we're using. So this is more like a remark to denote that this counting is not so it's not so straightforward to verify this character property. And so to put the to bring the analogy to the signature level, we also found that these linear functionals behave well with respect to the coproduct. So there is also a co-multiplicative property. So here we again consider interval partitions, and this time the operation happens on the interval partitions that really are indexed in this functional. So whenever we have that an interval partition is the result of the concatenation of two other interval partitions, then we can really split the counting. And here, so the notation I used is that, so clearly any interval partitions can be written so uniquely as these as this bullet operation applied on single blocks. Okay, these are the irreducible elements with respect to the coproduct, and we can write any interval partitions like this. That's why here you see this notation. So capital N1, capital NM, and small n1 and small nk. And then in this case, things again are become quite simple because of this operation we can iterate. So if the large guy is written as the concatenation of m blocks, we can simply iterate this the concatenation so that we have counting on single blocks, and we have seen that on single blocks this operation is just some combinatorial counting, so that we have just a sum of products of binomial coefficients. But it was a necessary step that we had to take to introduce these conjoined permutations patterns of algebra. And it took us actually, so we spent quite some time to understand this setting, even if the results are not incredibly deep, but we really had to figure out how to encode this and how to prove this. And now we can finally introduce the Hopf algebra on conjoined permutations patterns. So what we do is, so for the products and the co-products, we so the main operation, so which will then be dualized into a product, is really some sort of combination of what we introduced on interval partitions and the operation that Yannick introduced. So here we are really having the same indexing sum, but we are adding so we are now, so the underlying space is a space of pairs of interval partitions and permutations of the same length. And that's why we have to add this permutation term, and which needs to be standardized. Okay, so it's similar to what Yannick did. And so we see in this expression that we have both the permutation part and the interval partition. So the notation is quite simple. So before we add only squares, now we can really draw numbers. So one line notation with the adding of this block structure of this interval partition. And you see, so maybe this example is even too extreme. So if we take this 1, 2, we really see this restriction to permutation and also this gluing. And somehow the interesting thing is that if we do not consider gap, as I do here for this example with 2 and 1, we really have an operation that it's really close to what Yannick had, and it makes sense because somehow we don't want to have consecutive values here. So the behavior needs to be the same. And for the other operation, we have to concatenate, and it's quite straightforward in the sense that again it's a mixture of what we did on interval partitions and what Yannick did on permutation. So the first component is just putting side by side partitions, and the second component is doing the same for permutations. And it turns out that these two operations are compatible in the sense of bialgebra. So the proof of the bialgebra property so is very close to the others. So it seems to be almost a consequence. And yes, so we have that they form a connected filtered of algebra again. So since the operation, so if you dualize, the coproduct is filtered and this other is graded. And it's also commutative. So there is, again, this commutative characteristic. And it's interesting to see if so on this slide. So the first part is really so this Hopf algebra statement. Then we want to see if we can, for example, embed the Hopf algebra on permutations patterns in our Hopf algebra, and indeed we can, because we can see that the singletons partition trivializes whenever we consider singletons. So the gluing becomes a simple operation. So it's just the partitions of the union, the singleton partitions of the union of the underlying set. And so we can embed the Hopf algebra on permutation patterns simply by sending permutations to the singleton partitions and the permutation itself. And the same kind of phenomenon you observe also for the co-algebra part, in the sense that when you consider this concatenation, this singleton partition, you are not kicked out from this sub Hopf algebra. So we can really embed these permutations patterns here. We can also embed the partition of algebra, so the one I showed you in the previous section. And so the intuition is that we can send now partitions to all the pairs that has as first component the partition itself, and then we are summing over all possible permutations of that size. And it turns out that this behaves well with respect to the algebraic operation. So also this can be embedded. And so finally, we have again a signature. So we try to give a combinatorial somehow really description of these operations. And actually, so we found out that these patterns were already studied in the context of Mahonian statistics in this paper by Balson and Steingrimsson in 2000. And here, so what we need to add is the permutation pattern part. Okay, so we check for the fineness of the partitions, and then we check also that the permutations patterns is equal to sigma. And analogously, we have properties that are close to it, so that allow us to make the analogy with the signature. So we have a character property and also a chance type identity. And so yeah, we spent some time on interval partitions. Now conjoined permutations patterns, we were able to introduce these algebraic structures, but we still have to, to investigate more is of algebra. And one question that seems quite natural also because of what people are doing when they count permutations patterns is what can be done about, so can we count permutations patterns where we explicitly ask for a certain delay in time. So in this case, I want to observe 2, 1, but I want exactly one gap between them. And so is this possible? So can we count these as linear combinations of guys in our Hopf algebra? And the answer is yes, because the only thing that we need to do is to count patterns which are length 3 and are consecutive in time, and then make sure that the restriction of the first and the last are, so the pattern that we observe is 2, 1. So in this case, we would have 3, 2, 3, 1 and 2, 1 that are possible value, okay? Changing the value in the middle, so we would have a 3 here. And so it is indeed possible. And so to conclude my talk, so we have some open questions. So the article should be on archive next week. So we are still making some small modifications. And yeah, we are actually collecting questions. So one of my questions will be if there is a recursive formula for this product. So I was still not able to find one. And also, so we know from the literature on algebras that these two are free-commutative, but would be interesting also to have an interesting, so this is a vague question, interesting sets of free-commutative generators. So the most, so an example that most of the people know here is so Linden words for the shuffle algebra. And so another question would also be, so this product on interval partition as a shuffle part. So look like a shuffle plus something else. And is it true that it is isomorphic to the shuffle algebra? So if we somehow forget about the terms in which these overlaps occur. And so one thing that was inspired by this article that Yannick and Raoul was, so we still haven't found any interesting equations involving the antipodes of this Hopf algebra, and it seems so interesting and fascinating to find cancellations-free formulas for these antipodes. And the last question is, so these conjoined permutations patterns of algebra seems to be really like a combination of these two other Hopf algebra. So our Hopf algebra on interval partitions and Yannick's Hopf algebra on permutations patterns, and it seems to be like a mathematical phenomenon, so something that is also known, but yeah, we still don't know exactly what it is, and we would like to understand it. And yeah, so that's all I had to say for today.
Yeah, thanks a lot, Emanuele, for this very interesting talk. Are there questions or comments? So we had some questions already, they've been answered, but are there questions or comments?
Have you thought about this third point, about this relation to the shuffle algebra a little bit, or is it completely
So it was not the main focus, but I was interested personally. So since it seems, yeah, I also asked to the audience, maybe if someone has an idea. So I haven't really thought much about it, but I would be interested in answering this question somehow, because it really seems to behave like a like a quasi-shuffle, but then these overlapping terms, this recursion is more complicated. So yeah, I would like to see if there is the chance of writing this as a quasi-shuffle product, or
right. So I have a comment regarding the pattern aspect, kind of. So these pairs with the underlying interval partition and the permutation, that indeed seems to be like the pattern studied by Babson and Stengelson.
yeah.
And so they are now called Winkler patterns. Generalized pattern was a bit non-descriptive. And they're also so-called bi-Winkler patterns, where you consider adjacencies in values, not only positions.
Okay.
As well as they are both special cases of something called mesh patterns, where you have kind of a plot of the permutation and shaded regions that should be empty in the corresponding occurrence of the pattern. So,
but do they do also some algebraic combinatorial somehow? So we knew that this was already done, but we thought that the language we used was somehow not the same. So that's the element of novelty, or pseudo novelty from our side. But
yeah, I don't think so much has been done in that aspect. I mean, a bit in terms of the kind of, if you look at the pattern as a function, counting the number of occurrences of that pattern, you can view it kind of in the context of the so-called incidence algebra of the underlying poset. So you define a poset that one permutation of pattern is smaller than another if it occurs in it.
so what is the order relation?
So if your classical patterns is just that sigma is less than pi if sigma occurs in pi.
Okay.
Yeah, so it wasn't really a question, but just a comment.
Yeah, but thank you. So, and I didn't know actually that there was an incidence of algebra on permutations. So it's
yeah, it has been studied a bit at least. Yes.
Very interesting. Could you say the name again? Winkler or permutations or patterns?
Yeah, Winkler are the kind of originally generalized patterns by Babson and Stengelson.
Winkler is a name? Or?
No.
Vincular. I
was sounding too wrong now.
Vincular. Okay, I just tried to translate vincular. It says vinculaire.
Yeah,
okay.
So this comes from bond in Latin, I think.
Bond.
Yeah. Bond.
Okay. Interesting. Okay.
And the other was bivincular. If you have both kind of adjacencies in values and positions. And the last thing is mesh patterns.
Interesting. Yeah. Thanks.
Yeah.
Okay. Other questions or comments? Yeah, Kurush, about your question. So yeah, this somehow it is compatible. The product is compatible with the deconcatenation, so it is of this huge class of Verri, yeah, or I don't know. Yeah, it is B infinity, but yeah, much more we don't really understand at the moment. Whether I don't even know if there's hope of. So you have the easiest case is a shuffle. Then you have the quasi shuffle where you only merge two letters, but here you can merge everything. And I don't know if there's a simplification of that. But we're not sure. Okay. then if there's no further questions or comments, let's advertise with one final talk. No, this was the final talk.
This was in principle the final talk. The next one is scheduled for the fall session.
Yeah, exactly.
Nick Olsen Harris.
So, Emanuele, thank you for the nice talk. Thank you all for joining this semester. We had some very interesting stuff. It's always a pleasure, something I look forward to. And we hope to see you in fall again. Anything you want to add, Nicolas or Kurush?